there are many very different matrices that could reduce to this matrix. We let A be one of them. Now, for a little perspective, you start doing row operations on this matrix, and you can build up a wide variety of matrices A, or equivalently, multiply this matrix by a bunch of elementary matrices, and you can get all kinds of matrices A. But if you do that accurately, they will all reduce to this. Okay, now they're very different matrices with some significantly different characteristics, but they all reduce to this. Okay, well, first of all, if AX equals B, where X and B are regarded to be column vectors, probably real valued column vectors, then what are the dimensions of X and what are the dimensions of B? Well, clearly, if A is going to multiply X, since the rows of A will multiply X, the number of elements in the column vector X has to match the number of elements in the row vector A. So X is going to have consist of a column of 6 numbers, meaning it's going to have dimension 6 by 1. Now, what's the dimension of B? It's determined by the matrix. Well, B is going to have, it's going to be a column vector, and it's going to have how many rows? Of course, the number of elements it has is equal to the number of rows because it only has one column, but it's got to have 5 rows, 5 elements in the vector B. It's got to be a 5 by 1 vector. Why? Because you've got 5 rows here, and each row gives you a row of the B matrix. So the B matrix has to have 5 rows. It's got 1 column. It's got to be a 5 by 1 matrix. Okay, so now what's a basis for the row space? Well, first of all, let's be sure we understand what we mean by the row space. It's a space spanned by the rows of the vector A, not the space spanned by the vectors of this, although we're going to see that it's the same thing. Okay, so the non-zero rows of the reduced matrix are just linear combinations of the original rows, because any row operation involves doing a linear combination of 2 rows, or multiplying a row by a constant, which is a simple linear combination of that one matrix, or interchanging 2 rows, which doesn't change the set of rows that you have in the matrix. Okay, so since these are all linear combinations of the original rows or interchanged rows, we note then that the non-zero rows of the reduced matrix are all linear combinations of the rows of the original matrix. And they are also linearly independent, as we can see from the fact that there's no way you can do a sum of these 4 rows to get this row, because this row has a 1 in the first column and all the others have zeros. No combination of these 4 rows could add up to this row or add up to the negative of this row. So that implies linear independence in a way I'll let you think about. Well, you can say the same thing. The second row can't be a linear combination of the other 4, because the other 4 have nothing but zeros in the second column, whereas this one has a 1 in the second column. And similarly, this third row has a 1 here with zeros above and below it. It can't be a linear combination of the other 4. So they're linearly independent, and the conclusion is that they span the row space. So what can we say about the row space? Well, we got a couple of pretty good answers. They weren't quite exactly stated, but one was you have an R3 that the row space is an R3 space within an R6 space. And that was an excellent answer. It's not really an R3 space, it's isomorphic to an R3 space, and we'll find out what that means. But what we can say is there is, well, first place, the row space does have dimension 3, since it's spanned by 3 linearly independent vectors. Okay? So that means that we have a 3-dimensional subspace of R6. The row space is a 3-dimensional subspace of R6, the set of all vectors with 6 entries, 6 elements. Okay. So that's kind of interesting. So this tells us we have a row space spanned by 3 vectors, and that those 3 vectors are vectors in R6 because each has 6 elements. So we have then a 3-dimensional subspace of R6 after we establish that when you have a completely reduced matrix, any row with the leading 1 is going to be linearly independent of any other row. Okay. Now, what about a basis for the column space? Well, we've already seen it. The leading 1s in the rows correspond to column vectors that are linearly independent. So row 1, or column 1, column 2, and column 4 would be linearly independent. And that's true of the columns of the original matrix. Okay? So columns 1, 2, and 4 of the original matrix is a basis for the column space, the space spanned by the columns of the original matrix A, not the space spanned by the columns of this matrix, but the space spanned by the columns of the original matrix A. Why is that important? And we conclude then, of course, that since there are 3 vectors that span the column space, and they are linearly independent, which you can easily verify, that the column space has dimension 3. Same as, and so now we can conclude that the row space and the column space always have the same dimension, because you have just that many leading 1s. Whatever number of leading 1s you have in your rows, that's the dimension of your row space, and it's also the dimension of your column space. Okay, well, why is the column space important? Well, if we multiply A by this column vector, what do we get? Well, somebody said it, we get the first column. You can verify that. Take any matrix with, any M by 6 matrix with rows 6 elements long, and multiply by this, and you're going to get the first column of that matrix. Verify it for yourself. And then, if we multiply the matrix by this vector, which I wrote out in linear form, not as a column, but I used the semicolon, so clearly this is the column vector with a 1 in the second place and zeros elsewhere. You're going to get the second column, and if you do this, you're going to get the fourth column, which means that the vectors in the column space are going to exist over here as products that you get by multiplying this matrix by vectors in R6. Okay? Not only that, but you can prove that the subspace of R6 that's spanned by these columns is the subspace of R6 that corresponds to all possible products. Now, we'll say more about that later. That's an idea that's worth getting used to. Okay, so what I'm going to say then is the columns 1, 2, and 4 span the subspace of R5 you get when you multiply A by all vectors in R6. So you got R6, the vectors here. All these vectors are in R5 because all these vectors are 5 by 1. And all the vectors that you actually get here are linear combinations of columns 1, 2, and 4 of your original A matrix. Okay, so we're going to shift gears next and look at the span of a basis, or span of 2 vectors in R2.